Right, in this lesson, we're going to actually jump to the inverse side of this chapter. So to get to that, we first have to start talking about what's called injectivity. So we say that a function is either injective or one-to-one, meaning the exact same thing, if every output corresponds to exactly one input. So if you remember the definition of a function, that was every input corresponds to exactly one output. So we say it was well defined. If you put something in, you know where it goes out to. But you could have, for example, like the function f of x equals x squared. F of 2 and f of negative 2 are both 4. So that output of 4 actually has two different inputs. So a one-to-one function, that doesn't happen. Yeah, so it's kind of like a reverso definition of being a function. So we'll look here, we have these two functions f and g. You can check they are both in fact functions. And what we're going to look at here is just whether or not they are one-to-one. So if you have a look at the first one, what we'll see here is the output 9 only comes from -3. The output 2 only comes from 0. The output of -4 only comes from 1, and the output of 1 only comes from 5. So that one actually is a one-to-one function. And the second one, we're actually going to run into a little bit of a problem because we have that both -3 and 1 map to 9. So we actually have that this output 9 corresponds to two different inputs. So because of that, it's not a function. Sorry, it is a function. It's not a one-to-one function. Graphically, so because it's kind of a reverso definition, the way that we'll test a graph is actually really similar to how we tested a graph for whether or not it was a function. So let's say we make up a couple of graphs. And maybe I'll draw something that kind of looks like the example I'd used before. So this is actually what we'll call a trigonometric function, almost. It's not very symmetrical, but that's the idea. And let's try a different one. And let's go with and again, we can assume that it's xy as per usual, and that we don't really need a scale to answer these questions. So if you recall the vertical line test for functions, so remember the test for whether or not something was a function is if there's any vertical line at all that you can draw that crosses through more than one point, then it is not a function. So what we're going to have here for one-to-one functions, it's the exact same test, but it's the horizontal line test. So if any horizontal line crosses more than one point, need tense here. Any horizontal lines cross more than one point, then it's not one-to-one. So same test, what we're going to do is just draw a horizontal line. And you can see I can obviously draw this horizontal line on the first one that's going to hit a whole bunch of points, certainly more than one. So some line hits more than 1 point, and so our conclusion is going to be that it's not 1-to-1. And then if we have a look at the second one, doesn't really matter which horizontal line I try to draw here. Just work with me. I know they're not all exactly horizontal, but that's the idea. They all hit exactly 1 point on my curve. You might hit none sometimes, but they never hit more than one. So no line hits more than 1 point. And so as a result, this second one actually is 1-to-1. Right, so the test's very, very similar to testing whether or not something is a function. Again, the explanation is pretty much the exact same thing. As we can see here in this first graph, because this is hitting multiple points, what this means is that some y value, let's say that's y equals 2, is actually corresponding to multiple different x's. Right? There's maybe like x equal, well, I'm not labeling them, but you can see it's actually going to correspond to all these different x values. So it doesn't work. And then here on the right, if we look at this particular y value, it only corresponds to that one x value because there's only that 1 point of intersection. So it's very much the same idea. We'll just do one more example to cover the actual explicit function case, which is a bit more useful for us. So let's say f of x, I was going to write y, that's why my f looks so funny. F of x equals, let's say, 5x plus 2, and g of x equals, let's go with like x squared plus 1. So we can have a look at these. Yeah, so there's not like a quick test for this. The second one, what we could do is actually look at this one and say, I know that if we think back to what I was talking about at the start here, I know that g of 2 and g of negative 2 are both 5. So that thing's not 1-to-1, but I'm able to do that because I know that those numbers work. Well, how would you know whether or not those numbers are going to work? Not all functions are going to be, so clean as this. Not all functions I will have like previously just discussed a counterexample. So how we're going to deal with these is to actually kind of use the idea that this definition is just sort of like the reverso definition of a function. And so what we're going to do is actually kind of try to flip the variables. So if every output corresponds to exactly one input, what we're going to do is solve for the output. So in the first one, I'm going to let y be f of x. And what I'm going to do is solve for y. So what we have is y equals 5x plus 2, and then do some algebra, solve for, sorry, not solve for the output, solve for the input. The output's already solved for. Solve for the input. Yeah, y is, it's already solved for. There's nothing to do there. We're going to solve for the other one. That's what I mean. Yeah, so I'm going to solve for, again, scribble that out to make it very clear I messed up there. Solve for x, not y. Y is already solved for. There's nothing to do. So we're going to solve for the other one. And yeah, so just use algebra, move things around. y minus 2 equals 5x. So that's going to give us x is y minus 2 divided by 5. What we can see here actually is that this is a function. So x is a function of y. So it's in reverse, everything we want is a go. Everything that we want works well. So what that means is that our original y was actually 1-to-1. And so our function f of x is in fact 1-to-1. It does what we want there. All right, so on the other one, yeah, so it's gonna be the exact same thing. I'm going to solve for the input. Same idea, I'm going to let y equal g of x, and so what we're gonna get is y equals x squared plus 1. And again, I'm gonna solve for not y, I'm gonna solve for x. And so using my algebra, I'll move that over. Y minus 1 equals x squared. If you remember, when we undo that square, it's not just a square root. No square on that. It's that plus or minus square root. So what we've actually got over here is not a function. So that x is not well defined. It's not a function, and so that means that our original function y, or g of x, was in fact not 1-to-1. Or not injective. So yeah, it's a little bit harder to do it when it's an explicit written function, because you have to sort of flip it around and solve for it. But when it comes to the next conversation, which would be talking about finding the inverse, we're actually like 95% there if we've done this reverse, if we tried to solve for x. So basically in that case, the test to see if something is injective is almost all of the work to actually reverse the function, because yeah, that's what we did. Whereas in the other two cases, like plotting points or graphs even, there's a little bit more to be done to actually find what the inverse looks like.